We've all seen this picture before, but I chose it anyway because he's sitting in his office, and I have these very fond memories of sitting with him in his office. So I just wanted to put it up. So I'm going to talk a little bit about how, in my view, how Arakawa approached his science, and it has to do with how do we use models to learn about the real world. So one way is by actually creating the model in the first place, because you have to think about how does nature work and how do I formulate this and use it to create whatever kind of model it is, maybe a numerical model. And this happens before you start writing code. Another way is to compare the results of simulations with observations and see what looks good and what looks bad, and then try to understand why. And the third way is to do numerical experiments, like, taking out the Rocky Mountains or something. So any number of possibilities. So I'm going to come back to this later. I'm going to set it up now. And let's go back to grad school. So this picture was taken in the 9th floor penthouse in Belter Hall over that way in probably 72, maybe 3. At that time, all global circulation models were made in this country. They hadn't spread internationally yet. They were just starting to. The work was purely academic, in the sense that global models were not being used to do operational forecasting, and it was a little before they were used to do simulations of anthropogenic climate change. That was coming soon. Funding was relatively modest. The model developers were the same people as the model users. Today we have a small group of developers and a huge community of users. It wasn't like that back then. And it took about 2 hours on a fast, I put it in quotes because fast at the time, computer to simulate one day with a grid spacing of about 400 kilometers, which is very coarse by today's standards. This is a machine, or at least a type of machine, that I used as a student over in the Med Center, the old Med Center on the east side of Westwood Boulevard. It was an IBM 360 Model 91. It had 4 megabytes of main memory, 4 megabytes. It could do about 5.5 million multiplies a second. The disk drives held 2 megabytes, and they were about the size of a clothes washer, and they made a lot of noise. The input was via a card reader. Most of you have probably never seen one. And the printers printed a line at a time, so they were called line printers, and they made a hell of a lot of noise. And we didn't really have any graphical output. So computer...
For some reason, it's quite quiet. Maybe you could lean into the mic a little bit more.
I will. I will, and then I'll forget. Okay. Computer power has increased by about a factor of 100 billion. So from 5 megaflops to 500 petaflops, and actually, some of the machines are a bit faster than that now. 100 billion in the span of my career. It's absolutely astounding. We all know computers are faster, but this much faster? So this is a simulation. It looks like reality, but it's a very high resolution simulation. And during the same years as the machines were getting faster, the models themselves were tremendously improved, and this guy had a lot to do with that. So I'm going to show you this list of innovations, and I probably left something off, and I apologize if it's your favorite thing. And it's not quite in chronological order, but it's maybe slightly chronological. So I started with the Arakawa Jacobian. I won't read this list to you because it's too long, but many of these things, I think more than half of them, I'm going to mention again as I go through the talk. And this slide will appear again near the end.
They say that you can take this off, maybe.
This slide will appear again near the end. Okay, so the plan of the talk is I'm going to discuss some recent research in my group and point out the many ways in which it builds on Bakio's ideas. And the main subject, not the only one, but the main subject is going to be something called curl, which I will explain. It's a global model that's formulated in a particular way, and I'm going to try to walk you through the reasoning why it is the way it is. And here's a very cryptic diagram, which I'll show you again at the end with some labels on things, and I hope at the end of the talk you'll understand what this diagram means. So, when you build a model, you have to choose things, make lots and lots of choices, and certainly one of the first things, maybe not the first thing, is to choose the grid or the way of discretizing the sphere. Let me say it that way so I can include spectral models. The particular model that I'm going to describe to you uses a quasi-uniform, quasi-isotropic geodesic grid that's derived from an icosahedron by recursive subdivision of the little polygons. And so the resolutions that you see here go down to approximately 1 kilometer grid spacing, okay? You can, of course, go further, and this morning we heard from Masaki Sato about even higher resolution grids. So I mentioned here that back in the 1960s, Horikawa was involved in a project to investigate the possibility of using grids like this to build global models. So he was there really way back at the beginning. And you know, this is still being used today. It's being used in Japan, it's being used in Germany, and also in this country by MPAS at NCAR. You have to choose the system of equations. Now, you know, you might think, well, we know what the equations are. What do you mean? There are choices, and in particular, there are systems of equations that filter acoustic waves. This morning I asked John Thuburn about sound waves. So this paper, which came out in 2008, and is Horikawa and Konar, describes a particularly clever and accurate and simple sound wave filtering system of equations, continuous equations. It filters vertically propagating sound waves, but not horizontally propagating sound waves. So the Lamb wave that we all heard about in connection with that big undersea volcano a few months ago, the Lamb wave was there in the model, but the vertically propagating waves are filtered. And that's important because those are the ones that force you to take small time steps or to play numerical tricks so that you can take longer time steps. The only approximation in this unified system is that in the continuity equation, which is what you see there, the density of the air is replaced by the quasi-static density, and what that means is the density that you would calculate by integrating the hydrostatic equation with a boundary condition. So all you do is replace rho by rho QS, and everything else remains exactly the same as in the full compressible system. It turns out that this system, besides filtering the vertically propagating sound waves, conserves energy, which many other analytic systems do not, and is also more accurate than the other systems. So it's win-win-win. But like other analytic systems, the unified system makes you solve a three-dimensional elliptic equation, which can be quite expensive, especially with a very fine grid. So I'll come back to this. The next thing we have to choose is the prognostic variables. This means the variables that are actually time-stepped as the model runs. And here I want to connect with this Horikawa Lamb paper. It's actually a book chapter that came out in 1977. And the most widely cited part of this book chapter deals with the ABCD E-grids. Okay, so I'm talking about geostrophic adjustment and computational modes, actually. So on this geodesic grid that we've selected, there's a problem which John Thuber didn't really mention this morning. He kind of touched on it quickly, but there's something that I call the degrees of freedom problem. So Arco and Lamb in that book chapter advocated using the C-grid, which we've heard about earlier today. And simplest way to define the C-grid, simplest general way, is to say that a C-grid model predicts the outward normal component of the wind on each cell wall. So if the mass lives in each of these 7 cells here, on every cell wall, not just this one, but all of them, the model predicts the outward normal velocity on the wall, and not the tangential. So if you look at this, okay, let's look at the central dark gray cell. That's where the mass lives. It's got 6 walls. So there would be 6 velocity components on the wall, 6 outward normal components. But each one of them is shared between 2 cells, right? So there's really only 3 wind variables per mass point, but that's too many. There's only supposed to be 2. So there's too many winds. And what that means is that there'll be spurious computational modes in the wind field. So this is a practical problem. It makes the solution noisy, and it can cause trouble, especially when there's water in the model. So back in 1994, I was interested in using these geodesic grids, and I proposed a solution to this problem in which instead of predicting the winds, you predict the vorticity and divergence. This is called the Z-grid, and John mentioned it this morning. So in this case, it's an unstaggered grid. So the mass lives in the center of the cell, but so do the vorticity and divergence. So there's obviously 1 divergence and 1 vorticity for each mass, 2 degrees of freedom in the wind field for each mass. That's the right number. So degrees of freedom problem goes away. But the problem is we still need to know the wind. It's not enough to know the vorticity and divergence because we have to advect things. So to get the wind, we have to solve a pair of 2-dimensional elliptic equations on each model level. And that can be done, but it's a complication. And so I'll come back to this. When the Z-grid formulation that I just described is combined with the unified system that filters the sound waves, it leads to a 3-dimensional elliptic equation for the pressure. And this is something that most of you probably heard about. You know, it's characteristic of anelastic systems. So this complicated looking equation here, the delta pi, which you see right there, and again right there, is the departure of the pressure for some reference. And it's the unknown, and there's a forcing, which I didn't write out because it's messy looking, but there's a forcing on the right-hand side, and so you solve this equation for the unknown delta pi. And the problem is the boundary conditions, the upper and lower boundary conditions, are that in the case of a flat surface, d pi dz is 0 at the top and bottom. Those are boundary conditions that constrain the vertical derivative of the unknown rather than the unknown itself. And that can work, but it leads to slow convergence. Okay? So we'd rather have boundary conditions in which the unknown variable itself is constrained on the boundaries. So we'll come back to this. The way to solve the problem is to use the vector vorticity model. So here's another reference. First, before I go to the next slide, this is, of course, an extratropical baroclinic eddy, and this is a big cumulus cloud. And so here we've got vorticity in this sense, like so, and it's the vertical component of the vorticity that you're really seeing when you look at the picture. And here we have vorticity, but there's the updraft, and then there's spreading and sinking outside in the clear air. So the vorticity is like that, and the vorticity vector associated with this convection is actually horizontal. In fact, since the cloud is kind of cylindrical, you could imagine that it's something like a vortex ring, which I'll come back to, like a smoke ring, right? So it's wrapped around the cloud at each level. So the what I'm going to call the vector vorticity model was published here by Junhee Jung and Akio Arakawa in, I forget which year, but sometime around 10 years ago. They were interested in creating a three-dimensional cloud model in which the vorticity that you see in this picture was actually a primary prognostic variable of the model. So the idea now is that large-scale motions are primarily controlled by the vertical component of the vorticity, and small-scale motions are controlled by the horizontal vorticity vector, right, in the plane, on the sphere. Vorticity coheres. That's maybe not quite the right word, but vortices persist and can move. So they hold together, and it's kind of fascinating to watch them, right? We're all fascinated by that. Divergence disperses, gravity waves dispersing. So I intend this to be an aphorism, but realistic simulation of the vorticity is key for both large and small scales. So the VVM, this is the Arakawa and Jung idea, the VVM predicts the horizontal vorticity vector instead of the horizontal wind vector. So just to lay it out, if this is the three-dimensional vorticity vector here, that should actually be a capital V, but anyway, this is the horizontal vorticity vector, calling it eta, and this is the vertical component of the vorticity multiplying the unit vector pointing up. So here's what eta looks like. It involves the vertical shear of the horizontal wind, and it involves the horizontal gradient of the vertical motion. And that's important, the horizontal gradient of the vertical motion. And this is the definition of zeta, which you will know. So the VVM leads to a three-dimensional elliptic equation, but it's not an elliptic equation for the pressure. It's an elliptic equation for the vertical motion. And I'm not showing the derivation here, but basically what you're looking at here is essentially a form of the continuity equation, making use of the definition of eta. Again, I'm not showing the steps. So this looks kind of like a three-dimensional Laplacian of W over here, if you ignore the densities. And the thing on the right-hand side is the curl of the horizontal vorticity, del cross eta. Okay, so what the heck is that? But before we answer that question, if we assume the boundary conditions are W equals 0 at the top and bottom for simplicity, no topography, then these are Dirichlet type. So this constrains the unknown directly rather than its derivative. So this leads to a much better convergence of the iterative solver. And it's a major practical advantage of this. However, the VVM predicts the tangential component of the horizontal vorticity on each cell wall. Now, I need to take a minute to explain this complicated looking diagram. This is one grid cell, and so this is a vertical side, right? And it's hexagonal, as you can see. So here's a normal component of the wind on this particular wall pointing out, right, the outward normal. Here's the one on that wall, and so on. So we're showing 3 of them, we're not showing all 6. And eta, the horizontal vorticity vector, or the tangential component of it, lives above and below the wind. So remember, this is horizontal vorticity, it's doing that. So this outward normal here, you can think of as being associated with the swirling motion around this eta. Okay, I hope you can visualize this. So, predicting the tangential component of eta on the wall allows you to calculate the normal component of the wind half a level down, the blue arrow. That means it's a C-grid. So we're back where we started with the Z-grid that I described earlier. We had too many wind components per mass point. Now we have too many vorticity components per mass point. Basically the same situation. What we did in moving from C to Z, the C grid to the Z grid, is we replaced U and V by the curl and divergence of the horizontal wind. So we're going to do the same thing here. We'll replace the tangential component of the velocity on the cell wall, or of the vorticity on the cell wall, by the divergence and curl of the horizontal vorticity vector. It's the same idea, just translated from wind to vorticity. So here's how it works. And what I'm doing here is I'm comparing the Z-grid model on the left side with curl on the right. With the Z-grid model, we're predicting zeta and delta, which are defined here. With curl, we're predicting the curl of the horizontal vorticity vector, there it is, and the divergence of the horizontal vorticity vector. But the three-dimensional vorticity vector is non-divergent because it's a curl. So that means the divergence of the horizontal vorticity vector is minus d zeta dz. So what we can do, instead of messing around with del dot eta, we can just predict zeta and then calculate minus d zeta dz, and that gives us del dot eta. So what we actually predict are zeta and gamma, where gamma is this thing. So zeta relates to this, and gamma relates to this. And I'm going to say a little bit more about how that works here in a second. But first, let me comment, it's vorticity all the way. Okay. And Curl is a surfing town north of Sydney in Australia. So what is the curl of the vorticity? The vorticity has a curl when the vortex lines, which you can try to picture, make loops or rings. So for example, with this plume, and this is like the cumulus cloud I showed earlier, you know, there's rising motion here and sinking motion that you can't actually see around the outside. So there's horizontal vorticity, and it's making a sort of a loop around the cylindrical plume, like a smoke ring. There's a curl, okay? Here's another way. These are cloud streets. So the air is going up where you see the cloud, and it's going down in between the clouds. So the horizontal vorticity is like that, and it's changing in this direction. The horizontal vorticity vector is pointing either that way or that way, and it's changing in the direction perpendicular to its own direction. So it has a curl. So these are two examples of the curl of the vorticity vector that you can sort of visualize. And in both cases, the vertical motion comes into play very directly, okay? Here we're alternating between rising and sinking as we go from the cloudy region to the clear region. Here we have upward motion in the plume and sinking around the outside. So there's a very direct physical link between the vertical velocity and the curl of the horizontal vorticity vector. So how does it actually work? Well, of course, you have to give initial conditions. So we'll initialize zeta and then calculate del dot eta from this. And we'll initialize gamma. And then the way to get eta is to solve a pair of two-dimensional elliptic equations at each level, just like with the Z-grid model. Once we know eta, we do exactly the same thing that the VVM does. And I won't explain all those steps, but that's in the Jung and Arakawa paper. So that's how it works. And so it's a different grid. I mean, I didn't actually mention the A grid earlier, but the A grid has the two horizontal wind components and the mass on an unstaggered grid. So they're all defined at the centers of these cells. The Z grid, I did explain, zeta, delta, and H, unstaggered, all at the center of the cells. Now we have another unstaggered grid with zeta, gamma, and H, all at the center of the cells, and I want to call it the omega grid. Okay. So back to this diagram. Curl uses a geodesic grid, the sound wave filtering unified system, the vector vorticity model, and the omega grid. So that's what this picture means. And it works. So we built a global version of this thing using the unified system. And we tested it. I'll show you 2 slides with tests. Here it's a DCMIP test, so this is an intercomparison of dynamical cores that was organized by Christian Jabanowski and others. And in this particular case, you're simulating non-hydrostatic gravity waves. So results from curl, this is along the equator. Results from curl are shown in these left panels for 4 different times, starting from an initial condition. And here are results from Endgame, which is one of the models that John Thuber contributed to the development of, and that he showed some things from this morning. So the main point is they look quite similar. Here, they're, in addition to the color shading, there are contours drawn, and over here is just the shading. So it makes them look slightly different, but they're basically very similar. This is the very standard Hill-Suarez test, and you know, I'm not going to talk about this, but basically the results are as expected. So let me see how I'm doing here. Okay. Now I'm going to switch gears a little bit. This slide was created by Akio when he was thinking about global CRMs. He's very aware that computers are getting faster and people are interested in actually replacing convection parameterizations in models with direct simulation of the convection on sufficiently fine grids. So he made this little diagram in which the horizontal axis is model resolution. It's actually grid spacing. Okay, so here's extremely coarse 1,000 kilometer grid spacing. Here is a 100-meter grid spacing. This is similar to what Masaki was talking about this morning. The European Center operational model and the NCEP operational model are both somewhere around here now, getting finer by the year. So a GCM in the sort of old-fashioned sense would live over here in the hundreds of kilometers grid spacing area, maybe extending over into 50 or something. A cloud resolving model, CRM, lives over here somewhere, so grid spacing of on the order of a kilometer or 2 or finer, okay? And so what Akio was thinking about was how to get from here to here. So the vertical axis is the degree of parameterization increasing downward. So the GCM with coarse grid spacing, the convection is highly parameterized. And in the CRM, it's much less parameterized. You still have, turbulence parameterizations and so on, but it's much more nearly explicit. So we've recently started, 2 years ago, started a project at CSU called Earthworks, which I'm going to tell you a little bit about here. It's led at CSU by myself and Jim Hurl, and is supported by the National Science Foundation. It's 5 years to develop a global storm resolving coupled model that uses a single nearly uniform global grid for the atmosphere, ocean, sea ice, and land surface. And this new model is based to a large extent on CESM. So, we're not building this from the ground up by any means. So we're using CAM6 physics, but with the MPAS non-hydrostatic dynamical core, which lives on a geodesic grid. We're using the MPAS ocean model developed at Los Alamos by Todd Ringler and others, and I think that was mentioned a little bit this morning. So these 2 dynamical cores are formulated in essentially the same way, and the grids are the same. The grids can have various resolutions, of course, but our plan is to use the same grid spacing for both the atmosphere and ocean. There's also a sea ice model that lives on the same grid, so an MPAS sea ice model. And then, of course, there's a community land model. There's no dynamical core involved with that, but that has been implemented on the grid. And then there's a coupler, which now NCAR wants to call a mediator. I don't understand the reasoning, but anyway, this couples the various pieces of the model together. This is not a project of CESM or NCAR, it's a CSU project, but we are preserving compatibility with the evolving CESM code base, and we are engaging with the CESM community. This thing is going to be open source, and we're going to have releases, and you'll be able to find comp sets and GitHub and so on. So the idea is to create this as what amounts to an unofficial or maybe renegade version of CESM, in which the ocean model of CESM, which is going to be MOM6 in the next version, is replaced by the MPAS ocean because we want to use the same grid for everything. We have a nice logo that you see over here. This was designed by a graphic, an artist professional at NCAR. So one of these hexagons is the atmosphere, one is the ocean, and one is the land surface, and this just indicates that it's a global model. We have t-shirts with this. And as I said, all components are going to use the same model, so the same grid. So one grid to rule them all. And our target resolution is 3.76 or 3.75 kilometers globally, which is in the cloud permitting range, okay? Sometimes people call it storm resolving. Okay, now I learned recently that people call these models K-scale. I didn't know that. K-scale apparently means kilometer scale grid spacing, okay? It's kind of cute. So for the atmosphere and land surface, with a K-scale model, you can do, thunderstorms and things. You can do hurricanes with realistic intensity. You can resolve the topography pretty well. So Long's Peak in Colorado is resolved, at least crudely. Gravity waves of the type that Young June talked about this morning, orographic gravity waves, and also gravity waves forced by convection and other things. Coastlines, of course, are well resolved, so you can think about doing estuaries explicitly. Lakes and large rivers, so the Amazon would be resolved here, the Mississippi, and cities. New York City, pretty well resolved. Fort Collins would have a number of grid points. So. And for the ocean, you get the most energetic eddies, the mesoscale eddies, at least away from the poles. You get ocean deep convection, which only occurs in a few places, but it's important. You, of course, get the bottom topography. You get internal gravity waves, just like in the atmosphere. And, again, estuaries. So I'm going to show you a couple of results from Earthworks. What we've done is we've started with low resolution and just hooked the parts together, and that is a non-trivial thing. You might think, okay, we'll take the ocean model and click it in there, and we're done. But it has to fit into the CESM software infrastructure, and that took a long time for a very experienced programmer. But it's done. And then we started course resolution and worked our way down, doubling the grid, or cutting in half the grid spacing, and then running that for a while and then doing it again. And every time we cut the grid spacing in half, something breaks. Okay? So something is using too much memory, or there's some other sort of software issue like that. So we're finding all these problems that nobody knew were there, and they get fixed, and then we double the grid spacing again, and there's another problem. So we're working our way down. We are able to run the atmosphere model with a 3.75 kilometer grid on Cheyenne, which is the current NCAR supercomputer, just barely fits. But that machine is not our target machine. I won't talk about that here. We are currently running the coupled model with a 30 kilometer mesh, and I'll show you that here in just a second. These are some results from the atmosphere model, simulated an observed case. This is a forecast from observed initial conditions. Here are the observations from radar data. This is a calculated radar reflectivity from a version of the model that used wharf physics. And this is the same kind of thing from a version of the model that's using CAM6 physics, which is what's in CAM6. But it's MG3, that's Morrison-Gettleman version 3. It's the latest and greatest microphysics. And you can see that, the chem physics actually does a pretty reasonable job. I won't show a slide about this, but the convection scheme of Chem 6 stops convecting as the grid spacing gets finer. By the time you get down to maybe 7.5 kilometers, it's almost not doing anything. Now I'm going to show you two movies, and the one on the right will play first. They're the same thing, except that one of them was run on the 30-kilometer grid, that's the one on the right, and the other one was run on the 60-kilometer grid. So it's atmosphere and ocean on the same grid. And they're started with realistic ocean thermal structure, but no currents. And so the currents spin up early in the simulation. And what you're going to see is initial condition at day 65, starting from January 1. And in the case of the 60-kilometer grid, it goes out to day 220. In the case of the 30-kilometer grid, it goes out to day 230. This is just something to do with the way the movies were made. It's not anything to do with the model. So what you'll see is when I click is the right side movie will play, and you'll see eddies appearing along the equator as things spin up. These are called tropical instability waves. I don't know why the oceanographers call them that. It seems like a weird name. But, and you see that the northern hemisphere is warmed up because the seasons are changing, right? And the southern hemisphere is cooled off. Now I'll do the same thing with the 60-kilometer, the coarser grid on the left side, and same kind of thing. But the seasonal warming in the northern hemisphere is somewhat weaker, well, very noticeably weaker. So definitely differences in these two resolutions. So now the 30-kilometer coupled run shown on the right here has completed 2 whole years and a bit more, but I don't have results from the second year to show you here. Anyway, the point is the plumbing works. But now, you know, even with very high resolution like this, and now I'm thinking about the atmosphere model primarily, we still need parameterizations of small-scale dynamical processes. I say dynamical processes because, of course, we also need microphysics and radiation. But we need turbulence and shallow convection that's not resolved on a 3-kilometer grid. And Akio was thinking about this kind of thing as one of his last major projects. This brings up the subject of the gray zone. I think this term was used earlier today, and people talked a little bit about scale-aware parameterizations. So the issue is with scales larger than about 10 delta x, where delta x is the horizontal grid spacing, scales larger than about 10 delta x are reasonably well resolved. Subgrid scales, that is, scales that are below even 1 delta x, are of course not resolved at all, and therefore have to be parameterized, no question about that. But there are scales that are just slightly larger than the grid spacing, and we can say that they're represented because you can see them. You can make numbers on the grid for those scales, but they're not well resolved, which means the equations don't predict their behavior accurately. So in a sense, they have to be partially parameterized. And this came up a little bit in John's talk this morning. So the gray zone is the zone in which you don't have enough resolution to explicitly resolve the eddies. Let's say it's thunderstorms, okay? And the grid spacing is 10 kilometers. You can't explicitly resolve thunderstorms with the grid spacing of 10 kilometers, but they can try to grow in a kind of distorted way. But you also can't represent them statistically like with a parameterization because, maybe only one thunderstorm would fit in a grid cell. So, you can't do statistics in that situation. So you're between a rock and a hard place. There's no good way to go. This is what's meant by the gray zone. There's always been a gray zone. So when we were running atmosphere models with the grid spacing of 400 kilometers, the smaller synoptic scales were in the gray zone. Things like fronts and so on. With delta x of 40 kilometers, the mesoscales are in the gray zone. So squall lines and that kind of thing. With 4 kilometers, thunderstorms are in the gray zone, and with 0.4 kilometers, like we heard about this morning from NICAM, turbulence is in the gray zone. So it's always been there, and we're not going to get away from it. So we can think about creating, and this is what Akio wanted to do, resolution-independent parameterizations. The idea is you have one set of equations and one code and one name list, one set of parameter settings. And you can run it with a coarse grid, and you can run it with a fine grid, and it will do the right thing within the limits of the resolution either way. So it's very flexible and a flexible tool, okay? So we have this paper by Arakawa and Wu, and Chen Ming is here. So that's what this paper is about. And I won't say more about it here, but it's a really pioneering effort with very interesting results. The last thing I want to say on this subject, check my time, is to put a few sort of markers down for what a resolution-independent parameterization has to look like. This is what is often called scale-aware parameterization. And I'm going to call it resolution-independent, even though it's more letters. I claim that a resolution-independent parameterization has to be prognostic. That is, there has to be time stepping of the parameterization variables themselves, which really means that there's a memory in the parameterization itself. The current state of the parameterized physics depends in part on its recent past state. Okay? And one reason for that is that processes are not in equilibrium, particularly at high resolution. Quasi-equilibrium certainly doesn't apply with a grid spacing of 10 kilometers. And at high resolution, the almost resolved eddies, so eddies that can be represented on the grid but not accurately simulated, can undergo life cycles. That they can be individual cumulus clouds. So memory is obviously key there. Second point is that resolution-independent parameterizations have to be non-local. The state of a single column is not sufficient to determining what is happening in that column, because eddies can be advected or propagate between columns. And of course, we can all visualize things like this, propagating squall lines and so on. And a resolution-independent parameterization has to be very flexible. Deep convection has to be parameterized when the grid is coarse, but not when the grid is fine. And shallow convection and turbulence have to be parameterized with all resolutions, basically down to a few kilometers. So resolution-independent parameterizations are a very challenging model development problem. If you set this as a goal, I want to figure out how to do this. In the process of trying to understand that, you have to think about how nature works in ways that maybe you didn't earlier when you were thinking about very large grid cells. So we need to do a lot of thinking. And another question is, and this connects with the earthworks slides that I showed, are very high resolution models actually a good idea? If we compute everything, will we stop thinking? Because the model tells us what's going on, that's all we need to know. So here I want to lay out a couple of points of view that appeared in the literature recently. Here's a paper by Tim Palmer and Bjorn Stevens, who most of you will recognize. It appeared in Proceedings of the National Academy in 2019, and it's a perspective, okay, so it's an essay. And there's a little quote from the paper here. Simulations will stimulate theory by focusing efforts on the salient question of the underpinnings of predicted changes, rather than on the elaboration of parameterizations with little physical grounding. Now, as a parameterizing, I take those words, as a little challenging. Here's another paper, appeared slightly later by Kerry, who's here. This is in AGU Advances, and again, it's a kind of perspective. It's an essay that Kerry wrote. And here's a quote from him. Are we computing too much and thinking too little? The current desire to sidestep theory codified in parameterizations in favor of brute force resolution may prove to be the subordination of understanding to mere simulation. These are pretty strongly contrasting views, okay? And I don't fully agree with either one of them. I actually think we should be doing both, okay? So these guys are arguing they want to do high resolution and parameterizations have little physical grounding. Kerry's saying we should be thinking more and that theory is codified in parameterizations. In other words, the parameterization, in a sense, represents what we understand about the system. It's an idea, not just a curve fit. So, back to this. I showed you this earlier. List of innovations. Many of the things on this list I brought up. Some of the papers I actually showed you the cover page of. And I showed this before, too, near the beginning of the talk. How do we use models to learn about the real world? So Arakawa did a lot of rigorous model development, thinking very hard about what to do before writing code. Arakawa Schubert's a good example, okay? Arakawa Lamb, the potential astropeak sorting scheme that was mentioned by John, is a good example. There are lots of good examples. So for him, developing the model was a way to learn about nature. And I think it's a really good way to learn about nature. So that's what I mean by the journey is the reward, okay? In the process of developing the model, you learn, and that was the goal. You can learn, as I said earlier, by comparing the results of simulations with observations. He didn't do so much of this, especially with the global model. Okay? Not a lot of examples in his work of this type of thing. But he did do numerical experiments, not so much with the GCM. He did numerical experiments with cloud resolving models and used the results of those to formulate parameterizations of gravity waves and of convection, and so it's an interesting take. And the work that Steve Kruger did in his PhD work was one of the earliest examples of using a cloud resolving model to think about better ways to develop parameterizations for GCM. So Arakawa and his group were really pioneering in this area. So I wasn't going to show this picture because I know many of you have seen this before. This is 1972 NCART. I'm showing it because Jim McWilliams asked me to show it at lunch. So here it is, Jim. Akio is on the right, obviously, and I'm in the middle, and Wayne is on the left. Wayne looks the same now. And here's another one. So I really like this one because it's sort of a private conversation over lunch at a meeting, and that's what I enjoyed doing with Arakawa. That's the end.
Okay, perfectly timed. Any questions?
Mary Kay's going to have a question about that T-shirt stuff. The other one?
So regarding your proposal project and K-scale resolution, as a person from National Weather Service, I'm concerned about communication feasibility. So any thoughts on that?
The target performance at 3.75 kilometers coupled is, we think we can hit a little more than one simulated year per walk clock day on a sufficiently powerful machine. Machines that are available right now. So that's not fast enough to do IPCC style or CMIP style simulations, but it is fast enough to do lots of interesting studies of things like mesoscale convection and internal gravity waves and physics things that I personally am very interested in, and that we can analyze with a very high resolution global simulation like that. You really can't analyze it with observations because they don't exist. So that's the application, or one type of application. The other type of application is forecasting. So the team includes both climate types like me and weather types like both Skyrock. And we intend to make applications of both types here.
So you mentioned that the earthworks model with the current physics, the deep convection was mostly being done by the result scale. And there
Yes.
wasn't much,
Yes, on the sufficiently fine measure.
parameterized one. So is this a form, after that you touched on the need for scale aware parameterization, is this a form of scale awareness that needs simplicity or?
No, I have in mind replacing the convection and turbulence schemes in the model with something else, which I didn't talk about here. But that's the plan. And so there's still a grayscale and there's still a need for something better than Zhang McFarlane going to sleep. And so that's the plan.
Thank you for the talk. So regarding the three requirements about the resolution independent parameterization, I wonder if the prognostic will to some extent solve the non-local problem, because prognostic variables are already rapid.
I'm sorry, I'm not quite understanding. Can you pull the mask down for a minute?
I was curious about your three requirement about the resolution independent scheme, prognostic, non-local. Actually, I forgot the third one. Yeah, I was just wondering if the prognostic will, to some extent, solve the non-local problem, because if it's prognostic, it's already a rapid very numerics. So I don't need the column to be dependent on the other column next to it.
Well, convective systems are vector, right? And it's sub-critical variability that gives a vector value flow in addition to the mean state. So this happens in nature, and what I'm saying is, in the resolution of the parameterization, it's a total to do that.
Very nice talk, Dave. I just wanted to ask you, continuing on the line that you yourself started, a somewhat philosophical question. So on the purely practical side, you might divide the reasons for increasing the resolution of the climate model into two things. I won't mention both of these, but just to be clear. One is that you want to resolve phenomena that are of direct interest to predict, like mesoscale convective systems. You want to know what their frequency is, how it might change with the planet. The other is that you want to do better on things you already can resolve pretty well and may have for a long time. And so my question is that second objective being met? In other words, as we improve the resolution, are the things we've been able to resolve for a long time, like to take a trivial example, global mean temperature, getting better? The stratocumulus cloud bias, which was reviewed this morning, is it getting better? Do we have reasons to be optimistic about that?
Well, the stratocumulus cloud bias needs an increase in vertical resolution and probably also some better physics. So I certainly don't claim that that's going to get better just by increasing the horizontal resolution. But things like tropical cyclones obviously do get better as you increase the low resolution. So by the time you get under 30 kilometers, well, it's not realistic, but it's getting there. Okay, and so that's an example of something that we are crudely resolving today with our 50 or 100 kilometer CMIP simulation that we could do a better job on in the future with models like this.
I think there's one here, question there.
So in a traditional way of, say, developing the connected implementation or general implementation, so usually the process is that with a formulation, then put into a single column model, then test it, then put into a GCM. Do you think that this paradigm has to go, especially, for
The-
the single column test? Because,
Specifically the single column paradigm?
non-local,
Well, sometimes single columns use parameterized physics like Arakawa-Schubert, and sometimes they use CRMs. So in the CRM case, I think there's still room to use that paradigm, but maybe not the Arakawa-Schubert style. Yeah.
So you mentioned a little bit about, you sort of choose your equations that you want to solve and the grid and everything, and also related to, or maybe another aspect of the sort of scale awareness of parameterizations or parameters that you want to constrain. Do you think that there's a concern for something you'd have to think about, whether parameters of your model depend on your model choice in terms of the visualization method you choose or the prognostic variables you choose? Like, do you
Well,
think
what parameters are you talking about? So parameters in the parameterizations themselves, like in the microphysics, let's say?
for example?
Yeah. Well, I think, in my opinion, the right philosophy is that if there's a parameter in your model, it ought to be something that you can, at least in principle, measure. Maybe you can't really measure it, practically speaking, but in principle, it should be measurable. And then you should stick with your best measured estimate of that thing. So, I mean, Money-Novikov would be an example, right? We have, it's far from perfect, but it's definitely useful, and there are lots of numerical parameters in there, and they can be set based on measurements in Kansas, and then we stick with those values. We don't change them just because it gives us a better answer.
Dave, in your summary slides, you mentioned Professor Laika was not that interested in getting observations.
Yeah, I thought somebody would call me on this. Okay, so.
I mean, what he's thinking, he thinks the observation just too massive, but, he's basically know everything, when we take classes, he asks us to go to.
What I mean by this is that if you look at his published work, there aren't that many examples in which comparison of model results with observations are the main point of the paper. He does it, but the main point of the paper is the first bullet.